For our folio task, we're going to be looking at how we can describe scenarios that occur in the world, how we can model the rate of change with a function. So for instance, we might be interested in how an advertising campaign affects sales. And so if you understand the features of some of these functions, and we're going to look closely at surge and logistic functions, then you might be able to match what happens. So if we talk about the advertising campaign, you might say if there's a short advertising campaign that the audience may respond well, sales may increase rapidly, but then as the campaign's effectiveness decreases and is forgotten, that the sales gradually decrease. So that is basically the shape of a surge function. So before we go on to look at a particular scenario which you're going to choose in this folio task, we need to really understand the features of the surge and logistic functions so that we can model real-world situations. So part one is to look at the surge function, and you'll notice that it's in the form a pronumeral a, variable x, e to the minus bx, where a and b are positive. So there's limitations on our model. I'm also going to suggest that if you do some research to get guidance, you might find that they define the surge function as a x to the power p, e to the minus bx, for instance. So x also has a pronumeral, a number that we don't know. So it's a fixed number, we just don't know what it is. So we've got p as 1. So if you read other research, just make sure of those comparisons. So we've got a simplified surge function. So when you analyse the surge function, I recommend that you use something like Desmos. In Desmos, you can write down the general formula y equals ax e to the minus bx, and it will immediately ask you if you want the pronumerals to be sliders. And then you can explore what's a change one at a time. So if I go back, the first dot point, it says on the same axes graph the original function and the derivative function for a particular function, a equals 10, b equals 4. So let's do that. A equals 10, b equals 4. So there's the function, and just by looking we can see the maximum is approximately 0.25, position 0.25, and a value of 0.92. Then if you're going to do the derivative, you can find out the first derivative is 0 at stationary points. And if the slope goes from positive to negative, as visually you can see it does, that will be a maximum. And the maximum occurs where the first derivative is 0 at 0.25. So the first derivative can be used to determine some of the features. You might also notice that this function increases rapidly, so it's concave to its maximum, and then it reduces at a rapid rate, and then it reduces at a slowing rate. So where it changes shape from concave to convex, that's the point of inflection, and that's the point of most rapid change. So if we're going to use a surge function as a model, and we are aware in our real life situation where the greatest rate of change occurs, well then you want to design a function that has that value at its inflection. So I suggest that you draw it on Desmos and that you just take a screenshot screen dump of that and publish that rather than drawing it by hand. So we've already looked at determining the coordinates of the stationary point and the point of inflection and label it on the graph. So then when you repeat it for other values, I suggest that you display your results in a table. So you can write the function, you can write where the maximum occurs, and you can write where the inflection occurs. And then you're looking for a pattern so that when you get to the dot point, state the effect of changing the value of A, you can actually refer to your own data to support what you think is happening with the value of A. So remember, A is positive, so as A increases, what feature of the graph changes. And the same process, the effect of changing the value B. Now, we discussed in class the changing of B, so I'll just very rapidly show that to you. So I'll leave both the original function, which is red, and the derivative function orange. And if we, remember when B was 4, the position of the maximum was 0.25. So if we change B down to 2, and we look at the position of the maximum, it's very close to 0.5. It is 0.5. So when you've done a series of graphs and determined the position of the maximum while watching how B changes, you might come to the conclusion that the maximum occurs at the position x equals 1 over B. So 1/4 is 0.25, 1/2 is 0.5. So when you form a conjecture, you need to state it very clearly. You need to state the conditions that you are referring to. So something like for the function, so you've got to define what function you're referring to. And you could actually say surge function. And I'm using function notation. And you've got to write the conditions. So where the pronumeral A and the pronumeral B are greater than 0. And in actual fact, the model we're using, we're really only going to consider for x is greater than 0. So as you write your conjecture, you've got to write in that information. So our conjecture is for the surge function, ax e to the minus bx, under the conditions a, b and x are greater than 0, the maximum occurs when x equals 1 over b. Now you might recall that the way we determined the position of the maximum was from the first derivative. So if we're going to go and prove that conjecture, we will need to find the first derivative. And the maximum or the stationary points occur when the first derivative equals 0. And the stationary point could be a maximum or a minimum or a stationary inflection. So when you find a value, you're going to need to use a sign diagram of the derivative around that value to work out whether it's a maximum or a minimum. All right, so if it's positive followed by negative in slope, as we're expecting, then you will have shown that a maximum occurs at that point. This is just the first part of the folio task. The second part is to do a similar sort of analysis with the logistic function, and then the final part is to actually apply it to a scenario. So if we look at part 3 now, so I'm leaving you to have a go at part 1 and part 2, and remember, if you get stuck, you're most welcome to give me a call and we can have a supportive lesson around that.
Charles? Okay, that's good. Working out the derivative function for first principles, and then we use those results to come up with a generalised pattern for, so that's what you would have been working on last week.
Okay, so
if you've got a polynomial
let's have a look at part 3.
each term with its power, the power comes in front and reduces by 1. So you picked that up basically, you're happy with that? Yep. So we're going to be taking that to another level.
And I just want you to think about developing your scenario. So in lesson we talked about advertising, and at the start of this recording I also mentioned if we had an advertising campaign that we wanted to model that was just a one-off short advertising campaign, and then we looked at the results, we might predict that that will be modelled by a surge function. If we change the conditions of the advertising campaign, so for instance, if we had an advertising campaign that was ongoing and the sales reached a level that the ability to produce the goods was at an upper limit, that will be modelled by a logistic function. So if the sales get to a maximum and for some reason the demand is still up at that maximum but the supply is limited, that will be a scenario modelled in a different way. So in part 3 there are several situations that a logistic or surge function might be appropriate. You need to choose which scenario or your own, and you need to define your scenario sufficiently clearly to justify which function you use to model it. And then you need to perhaps do a small amount of research or and say these are the significant things. So if we've got an advertising campaign, let's stick with the surge model. If we have an advertising campaign where we get to a maximum sale and then the sales drop off, you might say maximum sales are reached 3 months after the campaign is launched, and the maximum sales are 5,000 items per month, and that the effect of the campaign reduces and the effectiveness is reducing at the maximum rate, I don't know, a year afterwards. Now, though, I don't like what I suggested, so, all right, but I'm just saying, make your scenario, mention the key features, and then you've got to model your function to match the scenario. So you've got to use quantities. You've got to quantify your scenario. All the best with this task.